Hello, this is Matthew from Studyclix. Today I'm going to walk you through this question 1 from the 2022 mock chemistry paper. It's a titration question. More specifically, it's the iron tablet titration, which you might remember from your redox titrations chapter. As you can see at the start of this question, we're told lots of information about the titration, how the titration's set up, lots of different masses and volumes relating to the specifics of the experiment that we're being asked about. But really we don't have to worry about those specifics until we get to the calculation section. Now, with these questions, the calculation section is really the part that you want to concentrate on making sure you get right, because it is the trickier part. Before that, you get questions about describing things to do with this titration, or explaining how you might set up different things, or why certain chemicals were used. These things are all stuff you can learn off. And really, if you understand these experiments, these titrations, then you will remember these chemicals. So I'll spend a bit more time on explaining the calculations, because I think there could be some more questions about that that you might want to have answered rather than the earlier sections in this question. So let me get into explaining these earlier sections first, and then we'll get on to the calculations. So we'll come back to this quick description before we do the calculations. Alright, so in part A, we're asked to explain, first, the reason for using dilute sulfuric acid for making up 250 centimeters cubed solution from the 4 iron tablets. And the answer that they were looking for part 1 was that the dilute sulfuric acid prevents oxidation of the iron 2 by oxygen in the air. Now, there's not much to be said about this, except for that oxidation of iron is called rust. So you probably know of this, just maybe you need to know what the chemistry term for it is. Now, if you did remember this, you get 6 marks, and those 6 marks aren't split up in any way, just either you get them or you don't. And then in A part 2, we're asked to explain the reason for adding more dilute sulfuric acid to the conical flask before the titration. And the answer they were looking for in this case was to fully reduce the MnO4-. Now, MnO4- is called potassium permanganate. So if you wrote MnO4- or potassium permanganate out in full, it doesn't matter, you get the full 6 marks. Now, these marks again weren't split up in any way for different phrases or anything, just 6 marks, all or nothing. And so part A in total was worth 12 marks. Now then, for part B, we're asked to describe the colour change seen at the endpoint. Now usually when I see describe in an exam, I'm thinking of writing something a little longer that's going to make sure that the examiner knows what I'm trying to talk about and what I'm trying to describe. However, when you're describing a colour change, there's really not much more to be said than the actual colour at the start and at the end. And with that said, the answer they're looking for is colourless to pink. So there's 2 parts to this, colourless and pink. You have to get them both right to get the whole 6 marks. Colourless, very important you don't say clear, because something can be colourless without being clear. A kind of foggy solution is colourless, just as clean water is, which will look what we would call clear. So it's the colourlessness that we want to talk about, not how clear it is or how foggy it is. So the answer we're looking for is colourless to pink, and there's 6 marks going for that. In part C, we're asked to explain why nitric acid could not be used to provide acidic conditions for this reaction. Now, in the description, we're told that sulfuric acid is used in this titration when we're making the solution and doing the titration. So that's what this question is really trying to ask. Why sulfuric acid and not nitric acid? Okay, so the answer they're looking for here is nitric acid is a strong oxidizing agent, so it would interfere with the redox reaction in this experiment. Now really all that you needed here was that nitric acid is a strong oxidizing agent. I'm just adding in the rest to maybe clarify to you why that matters. Now, as you might remember, this experiment is a redox reaction, or a redox titration more specifically. So if we start introducing these really strong oxidizing or reducing agents, the main redox reaction that happens might not be the titration, so we really won't get a result that correlates to the redox reaction we want to know about. So sulfuric acid is not a strong oxidizing agent like nitric acid, So the fact that nitric acid is a strong oxidizing agent is a reason not to use it in this experiment. Now, if you got this answer, you get 3 marks. And those are all the marks going for part C. Now in part D, we're asked to state one precaution that should have been taken as the endpoint of the titration was approaching. Then, we're going to explain how this precaution would have contributed to the accuracy of the titration result. Really, with these kind of questions, it shouldn't take too much learning off or anything. If you've done these experiments, all you really have to do is think back to what did I do in this lab. This question is one where there are several correct answers, so if you don't see the one you gave written out here, that's okay. And the one I gave is to add the potassium manganate dropwise. So if you didn't give this answer, you could also have given to swirl the flask or else to wash down the inside of the flask. If you got this correct, you get 4 marks. And then the reason why we would add the potassium manganate dropwise is so that the endpoint of the titration would be slowly approached and not overshot, allowing it to be identified accurately. Now, if you gave this answer or any valid reason for swirling the flask or washing down the sides, you get an extra 4 marks, bringing the total for part D to 8 marks. Okay, before we move on to part E, I want to go back and look at the description of the titration so that we can note these masses and volumes that we need to know. First, we're told that 4 iron tablets with a total mass of 1.4 grams were crushed. Then we're told that deionized water and sulfuric acid was used to make a solution of exactly 250 centimeters cubed. Next, we're told that the titration was carried out on 20 centimeter cube portions of this iron 2 solution, and that it was acidified with 10 centimeter cubed portions of dilute sulfuric acid. This was then titrated with a 0.005 molar solution of potassium manganate. And finally, we're given the average titration value as 27.6 centimeters cubed. Now that we have all these numbers noted, let's look at the first question in the calculation part, which is part E. We're told to calculate the number of moles in 27.6 centimeters cubed of the potassium manganate solution. So in E part I, we're asked to calculate the number of moles in 27.6 centimeters cubed of the potassium manganate solution. Now, how will we approach this question? Well, when we were going through the description of the titration and how the experiment was carried out, we were told that the potassium manganate solution was 0.005 molar. Now, what does 0.005 molar mean? It means that there's 0.005 moles per litre. And when we write it in this form with a fraction with 0.005 moles on top and 1 litre on the bottom, it becomes more clear what we can do with this. To find number of moles, we need to multiply 0.005 moles per litre by some volume in litres. Alternatively, we can change litres into centimetres cubed and then multiply by 27.6 centimetres cubed. Now, how many centimetre cubed are in a litre? Well, the answer is 1000 centimetre cubed. Now, that's something that's useful to remember, and there's really no other way to figure it out except remembering. It's useful because this kind of question comes up a lot, and knowing the conversion from litres to centimetres cubed just makes your life easier when it comes to these titration questions. So, if we multiply 27.6 centimetres cubed by 0.005 moles over 1000 centimetres cubed, we're going to get some value that's a number of moles. Now, why will this value have the unit of moles? Well, if we just take out the constant that comes before each unit and replace them with, say, a 1, it becomes clear that we can simply cancel centimetres cubed and we end up with 1 mole. This is a trick that works anywhere you're working with units, in chemistry as well as in physics. And if you're ever unsure if your answer is correct, maybe look at the units and see if the units work out correctly, because then at least you know you have an answer that makes sense in terms of what you're talking about. You don't have an answer in litres when they're asking for moles. So we'll just put this into our calculator, and multiplying 27.6 by 0.005 over 1000, we get 1.38 by 10 to the minus 4. And that's our answer for this question. And as always, when we write an answer in any science, we're always going to put our unit after the figure. So the answer here is 1.38 by 10 to the minus 4 moles. Now for this question, if you get the answer correct, you get full marks. In this case, there were 3 marks going for the question. So, 3 marks there. Let's move on to part 2. Okay, so part 2 asks us to calculate the number of moles of iron 2 solution required to reduce this quantity of potassium manganate. So to do this question, we're going to have to look at the chemical equation. So we'll go back to the question for that. And looking at this chemical equation, we can see that for every 1 mole of MnO4- there is 5 moles of Fe2+. Now when there's nothing in front of a chemical, it's the same as having nothing in front of an X in a algebraic equation. It means 1 of that. So we're going to use this ratio of 1 MnO4- to every 5 Fe2+ to answer the question. So we know that the ratio is 1 is to 5 is equal to Mn. So we know that the ratio is 1 is to 5 is the ratio of MnO4- to Fe2+. Now it's important to note that these values are moles. The reason is, when you're talking about a chemical equation, you're looking at the number of molecules that react with each other to produce a certain amount of molecules of other chemicals. Now, moles describe the quantity of a chemical in terms of the number of molecules, whereas mass describes the quantity of a chemical based on the amount of matter that's there. You might remember that from junior cert sort of physics. If you don't, just remember that chemical equations are talking about molecules, therefore the 1 is to 5 is talking about moles. Now, if we know that we have 1.38 by 10 to the minus 4 moles of MnO4-, how are we going to get to the number of moles of Fe2+? Well, in our little ratio, to get from the left to the right, we multiply by 5. So, if we set up a new ratio, to get from the left to the right, we're again going to multiply by 5. So, using this, 1.38 by 10 to the minus 4 times 5 should give us the answer we're looking for. I'm going to use the calculator to figure out what that actually is. Okay, and the answer I've gotten here is 6.9 by 10 to the minus 4. You'll notice I accidentally put in 1.38 by 10 to the 4 times 5, and I got a number that was obviously bigger than 1,000, 69,000 I think. So when I saw that, I looked at what I'd put into the calculator, saw that it wasn't the same as what I'd written in my equation, and just made that correction. So if you see an answer coming out of your calculator that is not what you expect, for example, we would expect a very small value for number of moles here, so when it came out with something that was in the tens of thousands, it's just a good idea to check and see, have I made a mistake here in plugging in, or is it a mistake earlier in terms of my actual calculations. So 6.9 by 10 to the minus 4. Again, you could just have this in decimal form, so that would be 0.00069. But I'll put it in scientific notation like I have it in the calculator here. And the unit there is, of course, moles. Now, there are equations that you could learn that would give you this answer in a sort of recipe way, that you always apply a certain equation and in a certain context to get the correct answer. But what I've done here is basically give you the reasoning behind those recipe type equations that would give you this correct answer in this case. So no matter what method you've used in this case, if you get this answer, you'll be getting 3 marks. Now, for part 3, we're asked to calculate the concentration of iron 2 solution in moles per litre, given that 20 centimeters cubed were required to reduce 28.2 centimeters cubed of potassium manganate. Now, as far as I can tell, that 28.2 centimeters cubed is not the correct value, considering what's said earlier in the question, but we don't really have to worry about that because that 28.2 centimeters cubed is not used in this calculation. So what we know is that 6.9 by 10 to the minus 4 moles of iron 2 were required to reduce the potassium manganate. And now we're told that this number of moles was in 20 centimeters cubed of a solution. So to find the number of moles per litre, we're going to divide by 20 centimeters cubed, and multiply by 1,000 centimeters cubed, because as we said earlier, there are 1,000 centimeters cubed in a litre. So if we think of this as we did this earlier question, where we put moles over centimeters cubed and then multiplied it by a certain amount of centimeters cubed, we can do the same here. If we put 6.9 by 10 to the minus 4 moles over 20 centimeters cubed and then multiply it by 1,000 centimeters cubed, we end up with a unit of moles, because the centimeters cubed above and below the fraction will cancel. So that's why we're going to divide by 20 centimeters cubed and then multiply by 1,000 centimeters cubed. So now I'm just going to do this on my calculator, and we get the answer 0.0345 moles. So this answer is in the unit of moles, but this is the number of moles in a litre. That's why we've used this 1,000 centimeter cubed factor. 0.0345 moles are in a litre, which means there are 0.0345 moles per litre. And how do we write moles per litre, but with a large M, molar? And if you got this correct, you get another 3 points. Now, for E part 4, we're asked to find the mass and percentage of iron in each tablet. Before we answer this question, I want to take us back to the main description that we're given at the start of the question to find some information that's going to help us here. So looking here at this description we're given at the start, we're told that there are 4 iron tablets involved and that they have a total mass of 1.4 grams. Now, further down, we're told that this ends up making a solution which has a volume of exactly 250 centimeters cubed. We're going to use these 3 pieces of information to get us the answer. Now, another important piece of information that we're going to use here is the answer from the last section, which was that the solution has a molarity of 0.0345 molar. So we know what the concentration of the solution is in a molar measurement, and now we want to find out what that means in grams per litre. So to do that, we're going to take the molar measurement of concentration and multiply it by the molar mass of iron. So we're going to have to go to the log tables to find that molar mass. Now, looking at page 79 in our log tables, at our periodic table of elements, if we look for iron, which has a symbol Fe, we see it here, and we see it has a molecular mass of 55.85. Now, 55.85 is the molecular mass of iron, but that also means that there are 55.85 grams in a mole of iron. Now, that's the quantity that we want to use, and we're going to round that to 56 grams. Now we have enough information to start going on our calculations. So we want to take our concentration of our solution in molar and multiply that by our molar mass of our substance. Now, sticking this calculation into our calculator, hitting S to D, we find a value of 1.932 grams per litre. Now, if you got this answer, you get 3 marks. Now you might be wondering how I knew to do this multiplication to get the right answer. And the way I'd figure this out if I was in an exam is look at the units, that I have a concentration in the unit of molar, which is a number of moles per litre, and then I also have a molar mass, or relative molecular mass, which is a number of grams per mole. Now if we write out these 2 units beside each other, we can cancel the 2 moles, and we end up with grams per litre, which is the kind of answer we're looking for, and so that's how I'd know to do this multiplication. Now for the next step, I'm going to divide this 1.932 grams per litre by 4 to find the number of grams in 250 centimeters cubed. So I just did that by using answer divided by 4. The answer button is very useful in an exam, it saves time, so use it. And we get an answer of 0.483. And the unit of that answer is grams per 250 centimeters cubed. Now if you got this answer, you get another 3 marks. And our final step to get the answer for part A is going to be dividing that answer by 4. Now why would I divide this answer by 4? Well, there are 4 tablets in this 250 centimeters cubed solution. So if I divide the number of grams there are of those tablets that there are in that 250 centimeters cubed, I'll find how many grams there are in one tablet, which is the answer divided by 4. And we get an answer of 0.12075. So we can think of that step as being a movement from how many grams there are in 4 tablets to how many grams there are in 1 tablet, since we know there are 4 tablets in 250 centimeters cubed. Now if you got this final answer for A, you get another 3 marks. Now those are the 9 marks available for part A. There's another 3 marks available if we get the correct answer for part B. And to answer part B, we're going to use all the information we have already gathered. To point out what information we're going to use this final answer for part A, and we are going to use the information that there were 1.4 grams of total mass and 4 tablets. So to find the total mass of 1 tablet, we're going to divide that 1.4 by 4. And putting that into our calculator, we get 0.35. So now we're going to find what fraction of the tablet's total mass is actually iron, and then turn that fraction into a percentage. So this fraction here is the total amount of iron in a tablet over the total mass of a tablet, and we're multiplying that fraction by 100 to get a percentage, which is just the standard way of finding a percentage from a fraction. Now sticking that into our calculator, we get 34.5%. And for this, we get our final 3 marks of the question. Now that brings us to the end of this video. I hope you found it helpful. Thanks for watching.